let's analyze this one and let's see if it's good or not, and then copy the next one and we'll repeat it and so on. Okay, so over here, this is something of the form P implies Q. So the original statement is this. So this is P, this is Q. Okay. So the statement has a form P implies Q. Now remember, how do we prove, normally how do we prove implication? What we discussed last time here in class was that one assumption would be assume P. So one alternative is assume P, then you argue, and then eventually you would like to say therefore Q. In other words, assume that P is true, and then eventually you would like to argue, start writing some stuff, and end up with Q being a true statement. Okay? So you could start by saying assume that AB is an even number, and then from there you start working until eventually you show that either A or B are even. Okay? That would be the direct approach. Now this one, it doesn't seem to be the approach that they're taking because it's saying suppose A and B are odd. Okay? So what are they doing? They are assuming something about Q. So this brings me to the second technique, which is one of the stuff that you should have read on Friday, which is proof by contrapositive. Okay? So what does that mean? Well, just remember that P implies Q is logically equivalent to negation Q implies negation P. Okay? So if you want to argue that this implication is true, you could do it by arguing that this one over here is true. Okay? And that's what they're doing here. Because if you focus on the contrapositive, that's an implication. So what we say is assume not Q, then you argue, and we want to therefore conclude not P. Okay? So that's how it would work. So let's see, what is not Q? So remember, Q is a statement A or B is even. What's the negation of that in words?
A and B. A and B.
So not A and not B, right? In other words, A is odd and B is odd. You understand this? The Morgan's law. So they started by assuming that both A and B are odd. So now that tells you, okay, they're going using contrapositive. They're using the contrapositive. Okay, so far that's okay. Now we need to argue. Somehow we need to end up with not P. That's what we want, right? So what's the negation of P? P is AB is an even number. So what is not P? That AB is odd. And at least we can see that the end result is consistent. Okay. So all we need to do now is check the in-between. If the in-between works, then this is a valid proof because they're using proof by contrapositive. Okay? So assume not Q. So in other words, A and B are odd. Okay? That means that A can be written as 2 times an integer plus 1, and B is 2 times an integer plus 1. Right? For some integer scale. That's what it means to be an odd number. Everybody okay with this? Okay, now all they're doing is they're multiplying A times B because we now have an expression. We can do it. Distribute, there's nothing wrong with the distributive property here. Everything works. Then these 3 times here, we can factor out 2. So we get that AB is 2 times an integer. So notice that this part right here is an integer. Why? Well, because both K and M are integers. So AB looks like 2 times something plus 1, where that something is an integer. That's exactly what it means to be an odd number, right? So you can conclude that AB is odd. And this finishes the proof, and it's a valid proof because it's a proof by contrapositive. Do you understand this? So number 1 is valid. Okay? Valid or good or however, whatever, or yes or no. I ask you to write yes or no. Okay? So this one is good. Are we okay with this? So again, just keep in mind, we're using here the proof by contrapositive. Okay? All right, so let us take a look at the next one. Okay. You know, every chapter, I mean, if you're not reading the book, you should really read the book because it's nice, because every chapter, usually it opens with this sort of investigate question where he doesn't give you the answer. He puts the question in there, he doesn't give you the answer, and then your job is, you know, after you read the section, you should be able to come up with the answer on your own, okay? And then find ways to verify, like talk to me or something like that. So, you know, it's pretty nice. Okay, so let's see. Here I can get 2 and 3 in one shot. So let me get 2 and 3 in one shot. All right, so let us analyze number 2. All right, so let's see. Number 2 says, remember the statement. The statement is here. If A, B is even, then A or B is even. So number 2 says, assume that A or B is even. Okay. So you see, here we are already assuming Q. If you notice this statement, this is what we want to prove. Do you understand this? Because the statement is if A, B is even, then A or B is even. So we want to argue that A, B is even. We want to show this. So if you want to show this, how are you going to start by assuming that A, B is even? Do you understand what I'm saying? So this one, but let's see, this one is saying, assume that A or B is even. Say it is A. Of course, because there's nothing special here about A or B. So when I talk about A, it's like if I was talking about B, okay? I'm just picking one. Okay, so A is even, but that's already fishy because that's what I want to prove. But let's read it. Okay, that is A is equal to 2K for some integer K. Yes, fine. Then A times B equals 2K times B, so it's 2 times KB. That's fine. Therefore, AB is even. So what did they just do? What they actually did here is they proved Q implies P. That's what they proved. Yes? They assume Q, and then they prove P. But that's not what we want to do. We wanted to assume P, and given P, we want to show Q. Do you understand this? So this is not valid. It's not good. I mean, of course, if you start by assuming that what we want is true, then you can make this work. Okay? So this is not good.
So basically, the problem there is that they started assuming the same thing that they were going to prove, but they did it wrong.
You know, it's if you want to show that this is black, you can say, okay, suppose this is black. You know, I mean, I want to show that this border is black. So don't assume what you want to argue, right? So that's so you have to be very careful when you touch the statement that you want to prove. You have to be careful what you say about it at the beginning because we don't know anything about A or B. Or the only thing that we know is that A times B is even. That's all we have to work with. Okay. So what they did was they showed that if one of the two is even, then the product is even. Yeah, okay, but that's not what I'm asking. Okay.
You can deduce Q from P, but you cannot deduce P from Q, right?
Given P, the question is given P, prove Q. I mean, given Q, you can prove P, as you can see here. Here, given that one of them is even, of course the product is even. Nobody's denying that. It's just that's not what I'm asking. That's not what the question is asking. So here they prove something else. What they prove here is that Q implies P. But I want to prove that P implies Q. Okay? So this is not a valid proof to the original argument. So this shows Q implies P is true. But this is not the question. So this is not the question. So this is not a valid proof. Okay? This doesn't prove what we are asked to do. Do you understand this? Okay? So I mean, you start assuming that what you want is true, then what are you doing? Then why are you arguing if you're already assuming that it's true? What you wanted to argue about? Okay? All right. So let's not valid. Does everyone understand that this is not valid? Okay, and the point is because this is really the converse of what we want, P implies Q. As you know, the converse is not the same as the original implication, as the original condition. It's only the conditional and it's contrapositive. Now, let's see what's going on with number 3. Suppose that AB is even. Okay, so we are assuming P, that's fine. But A and B are both odd. So what's going on here? What are we trying to do? So we are assuming P, and we are also assuming the negation of Q. Now, this tells me that they're trying to do a proof, another proof technique, which is called proof by contradiction. And we saw this at the very beginning when we did the square root of 2. In other words, we want to show that either A or B is even, right? So they're saying, okay, suppose that this has never happened. In other words, they're both odd. And then what they want to try to do is get to something that doesn't make sense, get to something that's false, a contradiction. If that happens, that means that your original assumption must be false. Okay? So if what you assume is false, then the opposite must be true. and the opposite of what we want. What's the negation of A and B both odd? That one of them must be even, right? Either A is even or B is even. That's what we want. So this, because it's given to us, so we can work with it. A, B is even. And now we are assuming the opposite of what we want. This tells me that we are trying to do a proof by contradiction. So this has the shape of proof by contradiction. Again, I'm working on the assumption that you read the stuff that I asked you to read. So this word should not sound strange to you. Okay? We're gonna do more examples after this. But this one is nice because it introduces many of the different techniques. So this is a proof by contradiction. Why? Because here we are assuming this part right here is not Q. Okay? So we're gonna show that not Q. So let me talk a little bit more about this. So we are assuming P, but we are also assuming not Q. So if we get to something that doesn't make sense, okay, something that's false, we have the following statement. We have question mark. Let's say that, okay, this is true. So, okay, let me put here a question mark. Let's say that we don't know the value of this, okay? But if we get to something that's false, we have the question mark implies false, and then we want this to be a true statement, okay? If you want this to be a true statement, what should be in this question mark? We have to put a false here. Do you see that? Because if I put a true here, then we're gonna have a problem because true implies false is not true. Yes? So that means this is the logic behind proof by contradiction. That means that we better have a false here to make the implication true. Okay, but then remember, this is my question mark, which is negation Q. So if negation Q is false, what can you then deduce about Q itself? It must be true, which is what you want. Okay, so it's not really a crazy idea to assume the opposite that I want. So I want to show that this water bottle is black. Okay, let me start by assuming that this is white, or green, or yellow, whatever it is your favorite color that is not black. And then you start talking and arguing and saying stuff. Because this is green, then this happened, and then this is gonna happen. And eventually, if you get to something that doesn't make sense, like, I don't know, 2 equals 3, for some reason, you end up with the statement 2 equals 3, or something that's clearly false, you know that something went wrong along the way in your argument. If you trust every single step that you did, the only thing that could have been wrong is this very beginning step, the assumption. Oh, then I assume, let's say it's not black, because if I say it's green, then you say, okay, it's not green, but then what is it? It could be something else. But let's say that you assume it's not black, and then you get to something that didn't make sense, then this is wrong. But if this is wrong, what is good? The opposite, which is, okay, this is black, it's done. Okay? So that's what's happening here. So let's read it and let's see, because we have to make sure that this is okay. But the structure seems good so far. Suppose AB is an even number, okay, that was given to us, but the conclusion, let's say, is the opposite. In other words, A and B are both odd. So that means A times B is 2 times something, times an integer, because it's even. But then A is 2k plus 1, and B is also 2j plus 1. Here, k and j are some integers, okay? That's what it means to be odd. So, let's see what happens. So if you do for some integers n, k, and j, then 2n is equal to this. Why is that? Okay, so they didn't put this, but remember, 2n is AB, right? So AB equals 2 times n, but then A is 2k plus 1, B is 2j plus 1. Okay, that's good. Multiply, you get this expression. Now you divide everything by 2, you get this expression. Everybody okay with this? Now, n is supposed to be what? What's n supposed to be? An integer. Now, what do we have on the right-hand side? This piece right here is an integer because both k and j are integers. But then you have plus a half. What happens if you do an integer plus a half? You're going to get a 0.5 in there. That's not an integer. Do you understand this? So we have an integer equals something with a 0.5. That doesn't make sense. So this is a contradiction. This right here, you see, this says that an integer n equals a non-integer. So this line here is telling you when they say which is impossible, that's what it tells you, okay, we have arrived to a contradiction, something that doesn't make sense. So that means that something must have been wrong. Where? In our assumption, because every line here makes sense. Given these assumptions, every line here works. Do you understand this? So the mistake is in the top. Now, you cannot say that this is not true because this is part of what we're given, that AB is even. So you don't touch this. So that means this is what's wrong. Okay, that both A and B are that they're both odd. That's the problem. So one of them better be, and that's exactly the conclusion that we wanted to reach. So we're good. Yes. So that's a valid argument. So this is a valid proof. So this one is valid. And remember, here when I say valid, it means a good proof. Okay, because you could have arguments that are valid, but they don't actually tell you the truth. Like the conclusion is not the truth. Okay. But here when I'm using the word valid, I mean it's a good proof. You okay with this? So that one is a yes. So 1 was a yes, 2 was a no, 3 was a yes. Okay? So questions? So we have seen proof by contrapositive, proof by contradiction. Let's look at the last form. So this one. All right. So let A, B be an even number. Okay, so they are assuming P. So far so good, that's not a problem. Say A, B is to N, and A, B an odd number. Say A is 2K plus 1. Okay, so here's another proof technique. Okay, this is how you prove an OR statement. And notice that this is what we want, right? So remember, the statement is assume P, prove Q. But what's Q? Q is the stuff that we want to prove. What is the want to prove? A or B is even. One approach of doing this, the thing is that when you assume stuff, that gives you things to work with. Okay? It's just you have to be careful what you assume. You cannot assume what you want to prove. That's the first thing. And second, you cannot assume too much, because if you assume too much, then yes, probably you can prove whatever you want if you assume a lot of stuff. But the idea is you want to assume the least amount of information that you can. So A, B is even, that's given to us. So we can work with it. Now you want to show that one of these is even, at least one of them. So when you have a statement of the form P or Q, and you want to show that this is true, one alternative is, okay, suppose that P is false. Why? Because this is giving me something to work with. So if P is false, what must happen then? For this to still work, then you need to show that that Q is true. So one technique is assume that one of the statements is false, and then you argue stuff, and eventually you want to prove that then the other one must be true. If you manage to do that, that's okay. Okay? Because you could say, okay, look, if P is even, if A is even, we are done. This is really the idea. So if A is even, we are done. There's nothing to prove because we already have what we want. Now, suppose A is not even, so it's odd. Then if that happens, then that means it better be even if we want this to work. That's what's happening here. Okay? So, so far, that idea is good. So AB is an even number. Say AB is 2 times n, and then let's suppose that A is odd. Our job now is to argue that B must be even, right? If we do that, then we're good. Because remember, there is an in-between line here that's not written, but it's explicitly there, that if A was even, we're done. Okay? So let's look at the interesting case, which is what if A is not even? It's odd. Because any number is either even or odd. Okay? If it's even, we're done. If it's not even, which is this case, let's see what's going to happen. Okay? So far so good. All right, so AB is even, that's 2n. A is 2k plus 1 because it's odd. Our job is to see what happens with B. All right, so A times B equals this expression, distribute. Now bring this guy over here. So we get that B equals 2 times this parenthesis. Now everything inside this parenthesis are integers, right? And it's an integer, K is an integer, and B itself is an integer. So B is equal to 2 times an integer. This means that B is even. Exactly what we want. So this is okay. This is a valid argument. It's a valid proof. Did you understand this? Again, this is another proof technique. When you want to show an OR statement, when you assume things, then you have stuff to work with. So one technique is, okay, suppose that one of the things is not okay, then you need to prove the other. But this gives you stuff to work with. By saying that A is odd, it allows us to write these things. Right? Because you know something about A. And the idea is that if A was even, you were done. There's nothing to argue here. So let's argue what happens if A is odd. Okay? All right. Are you okay with this? So this one is a valid one as well. So this one is valid. Again, when I say valid, I mean it's a good proof. Okay? More examples. Let's see. Proof the following. So for every integer, n, prove that if n squared is even, then n is even. We did this at the beginning, okay? We're doing square root. Let me just put all the statements here. 2 for all integers a and b, if a plus b is odd, then a is odd or b is odd. This form is kind of similar to the one that we just studied, but we're talking about product. Here I'm using sum, okay? So you may want to tackle this one by choosing one of the three good options that we did earlier, okay? So you just have to pick one. See if you can write it down. And then visit this one here. Verify P and P is 2, P is odd. Okay, let me write it down. So for every prime number P, either P equals 2 or P is odd. By the way, these are all the proofs that are in that section that I asked you to read. Okay, they actually worked out these examples. I mean, we do what we can, yes, but write everything. So there are no integers x and y such that x squared equals 4y plus 2. So number 5. So here I'll say determining if the statement is true. So when I tell you prove something, I'm already implying that it's true. You just need to find an argument for it. Okay. Now sometimes you don't know whether something is true or not. Okay. So that's what's happening in number 5. So 1 to 4 are true statements. You just need to argue. Number 5, I tell you a statement. You need to tell me whether it's true or not, and then justify your answers. Okay. So determining if the statement is true or not. Justify. In other words, sometimes you may need to justify with a full proof. Sometimes you may need to justify just by giving me a counterexample. You need to determine which one is. So if A is odd or B is odd, then A plus B is odd. And for all integers n, the number n cubed minus n is even. so let's see. We have 10 minutes. Let's see how much we can do in 10 minutes. Okay? All right, so the first one. First of all, try to see if you believe this. Let's try to first identify what technique. The first thing you need to do is try to identify what technique you want to use. So for every integer n, if n squared is even, then n is even. So this is a universal statement, right? So you have to start with an arbitrary number. You cannot assume anything special about n unless you use a particular technique. But whatever we do has to work for every integer. And then this is an implication. Is p then q? Okay. Now the direct approach would be assume n squared is even, and then somehow use that to show that n itself must be even. Okay. Now that well, if you assume that n squared is even, that would just tell you that n squared is 2 times something. But then to get to n, you will need to take square root or something, and then when the square root comes in, what do you do with that? That's a little bit weird. So if you try the contrapositive of this statement, it's easier. Okay. Equivalently, what we can do is prove that if n is odd, then n squared is odd. That would be the contrapositive. And if we manage to do that, then we're good to go. Now that's easy because if you know something about n, you can get to n squared by just taking the square to the second power, right? And when you take an integer to a second power, you still get integers. So that's nice. The problem with square root is that you can have an integer take square root and you don't get an integer. Square root of 2, square root of 5, square root of 6, that's not an integer. Okay? So taking square roots is a problem, but squaring is nice. It's fine. So that would be one alternative. Okay? So I'm going to go with that. So solutions. Number 1, I'm going to try by contrapositive. Okay, so I'm gonna show negation Q implies negation P. Okay, that's what I'm gonna prove. So remember, this is your P and this is your Q. Okay, so I'm gonna assume, remember this is an implication, so what do? You assume the first part, you're gonna prove the second part. So what's negation Q in this case? What is it? That n is odd. So assume, it's understood here that we should start by saying let n be an integer. Okay, whatever integer you want. So it's an arbitrary integer, be an integer. So I guess the line here that's implicit is, okay, if n is even, we're done, right? Because that's what we want to prove. So the interesting thing is, what if n is odd? Okay, so suppose n is odd, because if it's even, we are done. So suppose n is odd, then notice the structure. This guy here is my negation Q part. Okay, so suppose n is odd, then that means that n can be written as 2k plus 1 for some integer. Does everyone understand this? That's the definition of odd. That's what it means to be an odd number. Okay, now what I want to do is I want to somehow argue. It's always good to look forward and see what is it that you want. So you structure the argument that way. What is that we want to prove?
N squared is 2.
N squared is what? Odd. Remember, contrapositive. So P is that n squared is even. So not P, which is what we want to prove now, is that n squared is odd. Right? So given that n is odd, can I argue that n squared is odd? Well, all I have to do is let's look at n squared and see what we get. Right? So now that we have a formula for n, we can figure out n squared. It's 2k plus 1 squared. Yes? And compute. So what's this? That's 4k squared plus 4k plus 1. That's a good news, that little plus 1, because now we can factor out 2 in the first two terms. Why am I factoring out 2? Because I wanna show that this is 2 times something plus 1. And so far it's looking like that. The only thing that we need to argue now or say is this something. What must this be? An integer. Is it?
Yeah.
Why? Because k is an integer. So we're done. So n squared is equal to this. And then since 2k squared plus 2k is an integer, okay, you can say here, well, because k is an integer. So if this is an integer, then n squared is odd. So we argue the contrapositive, and therefore the equivalent statement, which is P plus Q, must be true as well, right? Questions? All right. So let's see. Let me see. Number 2 is similar. I'm gonna talk about number 2. I'm not gonna write it because I wanna pick something different. Okay. So number 2 is similar to the one that we just discussed. For example, I don't know. I'm gonna try the last one, the last approach. So I'm gonna assume. Let's assume that A plus B is odd. Okay. And then let's suppose that A is even. So what do we need to prove? I want to show that one of the two, A or B, is odd. If I'm assuming that A is even, what do I better prove? That B has to be odd, right? So let's see if we can do that. Well, if A, okay, so how do we do that? So let's see, AB is an odd number, and then A is even. So I want to show, okay, I have to write stuff down. I don't want to, but I have to write stuff down so you can see. Okay, so for number 2, I'm gonna assume the contrapositive is also very easy, but let me do it differently. So assume AB is odd, and also suppose that A is even. Okay? Let me write here. What do I want? It's in red. I want to show that B is odd. Okay, that's a plan. So, because remember, the statement is given that A plus B is odd, I need to argue that either A or B, one of them must be odd. Okay? So what I'm doing is, okay, given this, let's suppose that A is even, then I better get the other guys odd. Okay? So how do we do this? Well, A plus B odd implies that A plus B can be written as 2k plus 1 for some k. Yes? For some integer k. Then A even implies that A can be written as 2 times n for some integer n. Yes? Now, I want to say something about B. What am I going to do? I'm going to subtract these two equations. Why am I going to subtract? Because the A will cancel and I'm going to end up with B. Right? So, B is the same thing as A plus B minus A. Yes? Just subtracting the two. The A is cancelled. But remember, A plus B is 2k plus 1. And A is 2n. So now I'm going to collect these two guys together. So that becomes 2k. There are many ways to do this. This is just one way. The first thing that's coming to my mind is this. That's what I'm writing. Okay? So I want to use a different technique. So it follows that B can be written as 2 times k minus n plus 1. Yes? Now, okay, it has the structure of an odd number. We just need to argue what? What do we need to justify now? That this function is an integer. Is it an integer? Why? Because both k and n are integers. Right? So, it's an integer. So, B is odd. We're done. That's what we want. Okay? This one would have been much easier if we did contrapositive. It's just that then it would be the same thing that I did above. So I just wanted to show you something different. But just to review the contrapositive, who can tell me what's the contrapositive of this statement?
If A and B are even, then A plus B is even.
Do you understand this? Not Q implies not P. Now, if both A and B are even, what does that mean? That you're adding two even numbers, 2n plus 2k. What happens when you do 2n plus 2k? That's an even number. You can factor out the 2, you get 2 times n plus k. So, A plus B is even. Done. It's just that then it's kind of the same thing as what we did above. I just wanted to try something different. Okay? But when you're doing the problem, you do whatever you feel is easier. Okay? Like I said, there are multiple ways to argue. Are we okay with this? Let's see. And number 3, I'm just going to talk it out. Okay, this is an OR statement. All right? So suppose that P is any prime number. Now, this is an OR statement. If P is 2, we are done. Right? So suppose that P is not 2. Our job is to show that P is odd. How do we do that? Let's try it by contradiction. Well, suppose that P is even. What does it mean to be even? it means it's divisible by 2. But it's divisible by 2, then it cannot be a prime number, because by definition, what does it mean to be a prime number? It's only divisible by itself and 1, that's it. And if p is not equal to 2, then it better cannot be even, because if it's even, then it would be divisible by 2, and it violates the fact that it has to be prime. So it must be odd. Done. Do you understand this? Yes, I'm not writing it down because then it will take me time when I get to all stuff. All right. So that would be what you can do for number 3. You can listen to a recording.
Number 3 is valid.
Huh?
It's valid.
I mean, what I just told you was the proof. These are statements that you need to prove. I just told you the proof. Okay? It's just that I didn't want to write it down, not to waste time, because I wanted to look at 4, for example. This is a classic example of proof by contradiction. So there are integers x and y, such that x squared is equal to 4y plus 2. Okay? So in other words, we need to argue, is it there are or there are not? I think there are no integers. There are no integers, x and y, such that x squared plus 4y, so that x squared equals 4y plus 2. In other words, we need to prove that this equation does not have an integer solution, meaning that you cannot find an integer for x and for y that you put it here and make this work. Now, understand that there are infinitely many integers, okay? So this requires some argument. We're saying a big statement here, there's a big claim here, that you will not be able to solve this equation if you are only thinking about integers. That's what we're saying, okay? So, because there are too many integers out there, how do you go about this? Well, let's do it by contradiction. Suppose that you have an integer solution, okay? So, let me write that. So for number 4, so by contradiction. So what I mean by this is we're going to assume the opposite of what we want, okay? So suppose that there are integers x and y such that x squared equals, what is it? 4y plus 2. Suppose that you can solve it, okay? Suppose that there are integers x and y that I give you this. Okay, so then what can we do from here? Okay, one thing that I can do is the following. This means then that x squared is equal to 2 times 2y plus 1. Yes? What does this tell me about x squared? Then this means that x squared is even. Why? Because y is an integer. Right? Remember, we're assuming that both x and y are integers. We were able to find the integers that made this work. So then that tells me that x squared must be even because y is an integer. Yes? Okay, but if x squared is even, what do we know about x? We just proved something at the beginning. And x is even. That's proof number 1 that we just did. So then, by proof 1, x is even. Yes? All right, but now if x is even, I can come back here and I can rewrite the equation a little bit more. So let's see, if x is even, that means that I can write x as 2 times n for some integer n. Yes? Okay, so let's go back to the equation. So that means that 2n squared is going to be equal to 4y plus 2. So what is this? That's 4n squared is going to be equal to 4y plus 2. I'm going to divide everything by 4. So you get the statement n squared is equal to y plus a half. Do you see what's going on here? What's happening? What is this? N squared. This is an integer. So we have, because n is an integer, square is an integer, right? So we have that an integer equals some integer plus a half. This is similar to the things that we saw at the beginning today. So an integer cannot be something 0.5, right? So this is a contradiction. So this is impossible since both n squared and y are integers. For example, you could say move the y over here, and then you have a difference of 2 integers equals to a fraction, 1/2. What is that? That doesn't make sense. Okay? So that's a contradiction. So if it's a contradiction, what does that mean? means something went wrong, right? What went wrong? The original assumption. What was the original assumption? We are right to that problem because we started by saying that we could find integers so that this happens, right? So then this is wrong. So that means there are no integers with this problem. Do you understand this? And hopefully you see how we use the fact that we had integers, right? In here, it was we heavily used that. So there are no integer solutions. There are no integer solutions to x squared equals 4y plus 2. If you're gonna solve this equation, you need to look somewhere else, but you cannot look within the integers. Okay? So you're not gonna find.